near field probe, and other EMC solutions. So instead of just doing a short, quick demo of the product, I'm going to go over that presentation which we presented to IEEE, and that's the name of the presentation is Exploring EMC EMI Issues with Real-Time Scanning Technologies or Techniques. Here on the table, I have our scanner, our robotic arms, and the near field probes. Everything is live and working, and we can explore certain issues and then make a live scanning, and we can see the effect of these issues on the EMI, EMC emission of a board. So I'll start with who we are, just short slides. One slide about near field scanning, that's the core of our technology. And then we can review the near field scanning solution that we have, and then it will be a technical solution. We have several experiments here that we can go over and then actually test. We can discuss each one of them, or we can go to some experiment that will be more suitable for you guys, or we can just go over everything. So let's start. Who we are. So in general, we are developing near field scanning solution. Every company needs to pass the EMC EMI certification, and of course, we are providing tools to help you guys debug and prepare for that compliance test. So essentially, the tools are pre-compliance tools. The company resides in the UK. Software development, management, sales, marketing is done from the UK, but manufacturing and hardware development is done in Canada for historic reasons. We don't have sales people. We're mainly a technical company. We're working with partners across the world, and Innovate is our partner in India. Obviously, we see big benefits of using tools specifically to accelerate and reduce your time in chambers. We hope that contribute to a significant savings at the end of the development cycle. When you're going to a chamber, I'm sure you know you are actually measuring your DUT on the far field while we are operating on the near field. So it's quite different, and sometimes it's very complex to translate from near field to far field. It is possible in some cases. We have another product line, which is antenna scanning, and in the antenna scanning arena, we can translate the near field measurements to far field measurements. With PCB, it's slightly more complex. With the antenna testing, we can monitor the phase change across the board, and we compare that to the antenna performance, and we can actually predict the far field behavior of the antenna. It's very difficult to do that with PCBs. There's no unidirectional of the currents. There's a lot of phase differences. Signals are not coherent. It's a complex PCB. It's very difficult to predict the far field. However, the assumption is that if you see emission in the near field, just treat it. Most likely, it will cause problem on the far field. If you see a big spike of a certain frequency, it's better to handle that in the lab environment, change whatever you need, capacitors, terminators, add ferrets, and such, and that will increase your odds to pass the test for the first time, the certification process for the first time dramatically. So that's the idea behind the near field scanning technology for EMC EMI pre-compliance. Regarding solution in the market today, so there's no real solution. Let me try and turn on my pointer here. Pointer. Okay. Of course, you are going to the chamber and making your test. Before that, in the lab environment, many customers are building their own solution. Here you can see an example. Today, actually, any engineer can do that. It's not a big issue. The parts are widely available. This is a CNC-based solution, and of course, a set of near-field probes. Difference, they are scanning technology. It's essentially array of 1,218 or something like that probes, and the near-field probes, the robotic, the high resolution. I will review them later on. But the key factor here is the software, the EM viewer. All the instrument, including the near-field probe, can be connected to the same software, integrated. Everything is integrated within the EM viewer, including a camera, and that's actually provide a real benefits for the user, and you will see that on. So in general, we have two pieces of software, the EM viewer and the RF viewer. EM viewer is for the EMC, EMI product line, and the RF viewer is for the antenna characterization product line. These are the scanning solutions that we have. So we have the EMScanner, and that's the one that I have here on the table. We have the R version, which is high resolution. It's the same technology, but the R version is mostly used for high density PCBs and chips, silicons. Then we have the EM probe. The EM probe is a robotic arm with a single probe. It comes with our near field probe kit. The trade-off here that it takes longer than a scan, but it's not that something is better than the other. It's just a matter of use case. If you want to scan flat surfaces, the scanners are better. If you want to scan the component side, the near field probes and the robotic arm is a better solution. So it really depends on your needs. This is the near field probe kit. It's a set of 4 probes with a camera, 3 magnetic probes and 1 electrical probe. And of course, the camera is integrated, and this is the RF scanner for the antenna characterization. The near field probe. So the big advantage here is the integration of the camera. That allows you to see something like that in essentially real time. You just hover the probe above the PCB and you start makes the measurement. The kit itself is a handle, and that's connected to a spectrum analyzer. The next slide, we actually show the setup, and then you have the set of different probes, and you can replace the probe. We are tracking the probe based on this marker that you can see here. The camera recognize or identify the marker, and based on that, we can identify the probe and load the correction file. We can identify the position of the probe exactly and build the measurements. That's the setup or configuration. So we have the EM viewer, which is the application running on a PC. That PC controls spectrum analyzer. We support most of the spectrum analyzers. The spectrum analyzer that I have here is Rohde & Schwarz FSV. We have Regal, we have Siglant, and of course Keysight. We are Keysight solution partner. Keysight is our main partner. We're working very closely with Keysight, so anything that you need from Keysight, you can approach us as well. A camera, which we provide 5 megapixel zoomed camera with manual focus, but any camera can fit. Just a word about the camera. It's very tricky to find the right camera. Light conditions may vary, aperture, and of course the autofocus. We decided to go with the manual focus because with autofocus, in most cases, the camera focused on the PCB and not on the probe. And then we can't recognize the probe.
Sir.
Yes. Is there any question?
No, just okay, go ahead. Thank you.
Okay. And of course, you have the DUT here, and you can measure the emission with the probe, which connected to the spectrum analyzer. Very straightforward setup. As I mentioned, the EM viewer is essentially it's the software that support all the products, so you don't need to work with with only one solution. Here I have the scanner and the probes connected. However, I have only one spectrum analyzer, so I will have to switch the RF cable between the scanner and the probe when we will move to the live demo. That's the near field probe frequency response. Of course, based on the frequency, we have the 50, which will take you all the way to 24, 22 gigahertz. Then here it starts dropping a bit. And again, based on the frequency, different type of probes. This is the 00, which is the low frequency. That one, I'm sorry, all the way to 400 megahertz. So that's this information is provided in the datasheet. And of course, we compensate for that in the software. So when you're making the measurement, you're getting a flat response essentially, and the software knows that based on the marker. So if you switch the probes, we can identify that you are using different probe. That's the scanner. So again, based on the use case, you can decide if a scanner is a better solution for you, or the probes, or the EM probe. The scanner is very fast. Again, 1,218 H-field probes. Frequency range is up to 8 gigahertz, and the physical resolution is 7.5 millimeters. We are interpolate for half of that, 3.75. The scanning area is about A4. You can see here how it's done. It's really quick. I mean, it's almost real time. This is a GIF, a bit speed up, but essentially that's almost real time. And of course, we have different types of views. You can load an overlay, either a Gerber file or directly from a camera or JPEG. You have a 3D view. Again, things that allows you to identify the source of emission really quickly. That's the high resolution. You can see how we are making the measurements here with the high resolution. So we do have the native 7.5 millimeter resolution, but we are dividing each cell into two in each axis. So essentially making 4 measurements per cell. The next level up will be 16 measurements, because we will divide by 2 and 2 again. And so on and so forth, all the way down to 0.06 millimeters of resolution. So that's the high resolution, again, mostly for silicon and high density PCBs. That's the robotic arm, very similar to the near field probe set. It actually comes with the near field probes. Here in the video, oops, why did I lose my presentation? Okay, here in the video you can see a Beehive probe. Essentially, we are offering the 3D design of that adapter, and you can print to use any probe that you want. Again, the trade-off is the time. This is a single probe solution, so it takes time to scale. I think we are very close to the live demo, but a bit of some information about how to work with that, with the tool or with the software. So the first thing that you will do is actually a spectral scan. So you would like to see which frequencies are present in your DUT or emitted from your DUT. You can define the range of the scan, and you can define the number of peaks that you want to identify. Usually a customer will choose 2 or 3 peaks, the highest one. The next step will be a single frequency special scan. With that special scan, you will identify the points of high emission of that specific frequency. So you will take the frequency with the highest peak, and then you will scan. This heat map, it's not temperature, it's actually the distribution of the energy of that frequency wave across the DUT. And the red spots are points of high power or high amplitude. So most likely the source of the emission is around here. It's not always the case, as we know, RF is something complex, but in most cases you will find it here. The next mode of operation is a combined mode. Here we are scanning the entire range at every location. So it's a bit slower, but you can, after the scan, you can select or double click at the location and you will get its spectrum, or you can choose a frequency and you will get its heat map or the frequency distribution map of that specific frequency. And that we will use here. For the demo, I'm actually using the combined mode. It's just easier. It shows everything. Again, I'll show you that single frequency scan. You can skip that. Interleaved scan. So that's an interesting thing. As you know, magnetic field is actually a vector. We have two types of sensors, and also we have ability with the robotic arm to change the angle of the probe. So we can capture the entire orientation of the magnetic field and adjust accordingly. It's a bit more difficult with the handheld probe. You cannot do that, and that's the difference between a precision instrument like a robotic arm and a scanner to an handheld instrument. So it's not really repeatable, and the accuracy depends on the ability of the user more than a scanner or a robotic arm, which is very repeatable and very precise. However, also with the near field probe, you can get a pretty good results. Peak hold and peak detection, that's another thing that's very important. Sometimes you have intermittent interference. It's coming and going. There's no way to synchronize to that, and it's very difficult to capture. So the way we are addressing that is we're turning on a peak hold and a continuous run. So we simply continue to make scans until and hold the highest value until eventually we will start capture the interference or that it's very difficult to synchronize to. And of course, overlay, import Gerber, JPEG, or a live stream from the camera. And again, the near field probes, I'll show you that working live. If you need a bigger area, so we also support multiple units. And this one is very neat tool, just a report generator. During normal operation, you will do hundreds of scans. Not all of them are relevant. So we added here a very nice tool. You can simply select the tests that you want, and the tool will create a Word template and embed the results of the selected test to that template. Then the user will be able to go in and edit it, just to save some time for the users. Questions so far? Okay, so next thing is the demo board that I have here. For educational purposes, we have this demo board with 10 different experiments. And here we can show significant problems of a bad design, essentially, and how to solve it, and the effect of a capacitor, ferrite, current return loop, and things like that. So the first circuit that I'm going to scan is this one. Move that out of the way. So here we have a very simple circuit for a clock. We have ability to bypass a ferrite here and to engage and disengage a capacitor, and to change the current return path with jumpers. This is how it looks like in the actual software, and you can see the effect of a current return loop. I can go to the software now. go to the software now. So obviously I created a project here with everything. Let me close this one. And that's the software. So that's this is the scan itself, that experiment that I did just before. Again, I can run the scan now, and you can see how it's working, and it's actually building and scanning it. Now I'm going to change the location of the marker of the jumpers to eliminate the big current return loop, and I'll scan again, and you can see, of course, that everything changed here. You can see that most of the emission is actually around that area here, which is the oscillator itself. So you can see exactly where it's coming from. So that area. Now at that point, I can simply add a near field probe project. Go to here, turn on the camera tracking, select the camera, and now this is actually my the scanner, so I can move it to that area. I mean, we identify with the scanner that area has some issues. So at that point, I can put the near field probes and try to sniff around. Again, the scanner give us the results already, but just for the purpose of the demonstration, I can do that. Give me a minute to disconnect the RF cable. So now I'm connecting the cable to the probe itself. And you can see the probe here. So this is actually what's going on. As you can see, the green dots, the camera is tracking the probe, and we can start making the measurements. And I can simply move the probe around. I'm sorry, I have a connector here that bother me, but I need to work around it. And then we can actually sniff around and make the measurements, and the software will build everything on top of that. So let me start the scan itself. And that's exactly how it's working. So we're making the measurements, we identify in a precision way the area that's responsible for the emission. And actually that's the way. Now, this is obviously less accurate than the EM probe. It's essentially based on the user itself. But essentially, that's the way that we are working with the probe itself. Again, all the software is essentially integrated. Here you have all the projects. So that's the handheld probes. This is our the scanner one. And again, the handheld probe. There is a big difference between the handheld probes and the scanner, because if I'll show you the camera again, so obviously with the handheld probe, we are measuring the top side, the component side, while the scanner scans the bottom side. Again, there's nothing, I can't say which side is better. That depends on the PCB structure. In some cases, you might have a ground plane. If you have ground plane, obviously the scanner will not see a lot. It will be shielded. Then you will need to use something like handheld probes or the robotic arm. If you want to scan the bottom side, if there are some traces there, the scanner will see them. If you have above them a ground plane, the near field probe will not see them. Again, the bottom traces will be shielded. So that's the example. We can go over other area of interest. For example, the importance of return path here. Is there anything specific that you would like to see out of that that list. Let's go back to the first slide.
Yoram, I've got a request.
Yeah.
So some of the guests would like to see the setup. So I'll move my laptop and then I'll put my camera on and then they can see the setup, how it's done.
Okay. Maybe I can. Maybe I can join from the phone.
Yeah.
Okay, so let me stop sharing. That's okay, I'll handle that. So I hope you see the screen, but that's the setup itself. So this is the handle probes here, and that's the FSV that I'm using, and the camera is essentially this guy right here. I have a tripod, and it's connected to here. Robotic arm is also ready, but not connected. And this is what I mentioned that I have on the bottom line is a VNA, so I have only one spectrum analyzer connected, so I need to change the RF cable from the scanner to the probe. Cornell just gave us the near field probe case itself, so this is how we ship it to customers. And so it comes with a nice box, and we have a this is how it looks like. Okay, I feel like a model here. Now,
Thank you.
any questions about that? Okay, so let's move to actually experiment number 3. I think this is a nice example of near field probe use. Where is it? Okay, so in some cases you need to identify a trace. So obviously the scanner will do it in no issues. The trace here is on the bottom, so the scanner will give us a better result. So let me just connect everything again, and we can run that experiment. So here we have several traces, and just a signal, the same clock that going through and passing only one of them. The other one are not active. And the idea here is how to identify and follow a trace. This is how it looks like. And we go to the software itself, and that will be that experiment. And again, I can simply run the scan, and again, see that immediately. So obviously here you can actually follow the trace. So again, that's the scanner, and I can even zoom in a bit more here, and then we can really identify the current carrying trace very easy. We can do the same thing with the handheld probe, of course. So I just need to move the camera, the probe to here, and I'm going to change the RF input to that. And I can start the scanning. So again, just simply will capture that, and here I will see the areas, and that's even enough. Immediately you can see the. I just scan it for a minute, and immediately you can see the location of the current carrying probe. So this is how it looks like. So it practically took 2 seconds.
Yoram, I have a question.
Sure.
Can we get both phase and magnitude using the scanner?
That's a good question. No. Well, yes, in the antenna measurement tool, but no for the EMC scanners. The reason is the far field prediction or algorithms. To do that, we need to calculate the phase. For EMC EMI, we don't need the phase, and it will be very difficult to see the phase in a PCB. It's not like an antenna. I can share a few examples if you give me a minute. Oh, it's not on this computer. Yeah, I'm sorry, it's not on this computer. So with the antenna characterization tool, it will be very, not very easy, but it's actually implemented. We have reference antennas, and we can track the phase distribution. We're not doing that for the EMC EMI product line. Any more questions? Okay, so we can continue. Do you want to see? Guys, any input from your end?
Can you hear me? 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 Okay.
Okay, no questions. So one more thing I would like to show you, and that's this experiment. So this is essentially a design mistake that many people can do, and we really see a lot of issues with that. And this is a signal trace which is close to a slot in the ground plane, on top of it or close to it. Essentially, this is like an antenna that radiates like crazy. And here again, we have that experiment, so I can show you guys the the results of a trace, which is essentially running on top of a trace of a slot. I'm just moving the RF source, the signal, and you will see the results. So this is how it looks like. As you can see, the frequency here coupled with the slot and the ground plane, and it's really radiates. So we can go back to the software. That was experiment number 5, and again we can simply make the scan. Oops, that's not what I expected. Did I lose the signal? Maybe I lost the signal. My signal source died. Again, I can easily check what's going on. So now I can do a spectral scan to see if I have any frequencies present. And I lost my signal. Why I lost my signal? Okay, so let's get back to the presentation. Anyway, you can see here the difference between the results. Yeah, for some reason the Y.I.C here stopped working and I'm getting no signal out of it. Well, at least you can see it's live demo, so things can break. So at that point, again, I would like to ask you, do you have any question? Is there any specific things that you would like to see with the scanners, with the software, and with the arm probes? Nanda, anything from your end?
I'm good. I'm good.
Good. Okay, so
Yeah. It can be more interactive in case if any of you have got any specific questions, you can please ask. Yoram can answer.
Okay. So I can continue and review the presentation. There's only a few slides, so at least it will give you some insight. The next topic is actually crosstalk at a micro switch. These micro switches are being used in many boards and application. However, from isolation perspective, they are not very good. You will see coupling between them. I can go to which number was it? That was number 6. So I'll show you previous scans. And this is how it looks like. So even though we are selecting a certain switch, you will see coupling energy. It's not blue here. So it is coupled to the other traces. In addition, in this scan, in this scan, that's the return. That should be the return current, and you can see that it's create again a loop here which will radiate. So again, needs to be very careful with these deep switches. Another issue that you are using is shields. We're all using shields or enclosures. Again, sometimes every little gap in the shield can radiate and emit. You can test and measure the emission coming out of the shields again before going to a chamber. We had an incident with a customer that changed the handle of the enclosure from just regular handle to a pop-up handles, a handle that you push them a bit and they are popping up out of the enclosure, and that caused them to fail the certification test. So again, any shield or any enclosure needs to be thoroughly verified before going to the shield, to the test. Traces on board edges. Specifically, if it's a metal edge, if it's very close to the enclosure, it will couple with the enclosure and it will radiate outside. So be very careful with that. We had actually a problem with our boards. Again, I can actually share that information. So we have a slot, a ground slot in our boards, and there are two traces close together, so that's considered to be as an edge. And these two traces coupled with each other. The other half, one half of the board is RF related, the other one is digital. And we saw some frequencies from the digital side at the RF area. The reason was two traces which were a bit closer to each other around the edge of the board. So again, when you're designing boards, you need to pay attention for the edge. Filter behavior, again, very easy to check. With this demo board, you can simply bypass and add and change capacitors or resistors, but also in your unit, you put the DOT, you run a scan, very easy to change capacitor in the lab environment, and you know exactly how your board behaves. Even if you will have an issue in the chamber, again, you saw that before, you will know how to fix it. But that's the idea. Another thing which not really a problem, but the scanner, the near field probes, we are measuring emission. So anything that emits radiation or frequencies within the range, we can measure. So this is NFC. We can talk about charging devices. There's a lot of interest around wireless car charging, but unfortunately, this is way too much power for us. We've been approached by several companies, but they're talking about 10 kilowatts, 14 kilowatts, which is not suitable for that device. But any other charging station with a reasonable power, our power limitation is 30 dBm. If we can absorb that, so no issue with that. And that's it. We're done with the experiment. So at that point, again, I will ask you if you have any question, and if not, I will let Cornell.
Yeah, me again. So I've emailed you the presentation for the RF scanner that you were looking for.
So if any one of you have any
Anything else from anybody else? I think that's it. So, okay, so I'll end off the meeting by saying thank you very much, Yoram, for presenting and showing us how the solutions work. Really appreciate that. In the meantime, if you guys have any other questions, please feel free to email us or to email Innovate and the team, and they can send it to us. But we will get back to you if you've got any questions about any of the solutions that you saw here today.
I have one thing to say.
Yes.
I have one thing to say. See, this demo kit they have shipped it to us yesterday, so it will be available next week. In case if anybody wants to see the demo, please contact Innovate Electronics, either Hyderabad sales guys or Bangalore. So we would be very happy to come and
Fantastic.
test it. You can test it.
Brilliant. Okay, yes. So Nanda and his team will have the demo kit there. So get in touch with him if you would like to see it. I've got two more questions in the chat room, Yoram, if I may. If I want to make the near field probes as an energy injection device than receiver, is that possible?
Actually, yes, that's a good point. Also, the scanners, and we have another piece of software called EMViewer-IM, and that will allows you to select an area and define the time that you want to transmit to that area. So both the scanner and the near field probes are actually bidirectional. Instead of spectrum analyzer, you will need a source. But essentially it's bidirectional.
And then we've got another question. Can you show us the physical equipment again? So would you mind switching your camera on your laptop, Yoram, and just showing the equipment again?
Yes, and I saw another question there. So yes, I did mention the IM. So it's EMViewer IM. It's just another piece of software. And let me, okay, I'll disconnect this here. Camera. Just a minute. I'm going to turn my camera on here. Come on. Sorry, I'm just need to turn the camera on. Oh, I think. Yeah, do you see me? So that's the equipment. Do you see it, Kuna?
We do, yes.
Okay. So again, the scanner, the probes, and the camera above, spectrum analyzer here.
Can you show?
That's the camera. Okay, do you see the camera?
Yes, we can see. So the camera has to point on to the probe, Nanda, so that it picks up the marker on the probe. So that's why the camera has to be on top of the device that you are testing.
I don't know if you see the probe closer, because I don't see what I'm showing, but that's the probes.
Yeah.
And of course, each probe has a different marker. So you can see the two different markers here.
Yeah. So with every kit, there's a camera for probes. Okay. Any more?
Yes.
Yes, good. Go for it. No?
Yeah, I think. Yeah, I think that's it.
That's it. Brilliant. All right. Well, I'll take this opportunity now to say thank you very much for joining. It's a great solution for customers who, struggle to get budgets for the higher value product. So please get in touch with Nanda and his team, or with us if you need our help on anything. Yes, this will be or have been recorded. So I'll send that again to Nanda and his team if you wanted to revisit anything that we showed on this meeting today. So thank you again. It was lovely to talk with you.
Yeah, hi. There is one question with me. Can you please take it? This is Raj.
Yes, of course we can. Yes, of course we can.
Yeah. So one doubt is that can we upload these data get the data with phase and magnitude for the data in entire frequency spectrum?
I'm sorry, I didn't get it.
So basically the near field. Okay, the near field data which we are recording, can we actually take the data and then use it for some other purpose? So can we record the data in phase and magnitude? Both phase and magnitude information should be obtained in this. Is it possible?
Yeah, you can export the data either as text or CSV, and then you can manipulate that the way you wish.
Okay, whether it will have both phase and magnitude, whether that data?
Not with that data. We don't have phase here. We have magnitude, frequency and magnitude. Okay, with the antenna device, we do have, yes, with the antenna device, we do have phase.
Okay. So you can get near field phase also with that antenna?
The other one can, yes.
Okay, fine. So, I'll also check what I'm done. Yeah.
Yeah, so it's this one, right? It's the RF scanner. So the RF scanner, that device has phase measurement as well. So it will give you the phase measurement, the gain, the efficiency, the total power, the TRP. So you just place the antenna in the middle, you run the scan, and you will get all the information. I don't know if that picture here is good enough, but this is what you see. This is what you get. So that's the far field, and here you have cross section. Here you have the TRP measurements. So this is everything, but this is the antenna characterization tool. This is not the EMC EMI.
Oh. Okay.
Mr. Rajesh, from which company you are from?
We are from ARI.
Okay, great. Sir, we have already
automotive research.
Understood. We have already supplied this RF scanner. It is to measure antenna.
Okay.
We will share you more information. We can give a reference of whom we have supplied. And if it is really required, we can arrange to see the unit also.
Yeah. Yeah, and I apologize. I'm using the lab computer here, so I don't have all the information.
Yes, thank you.
For attending. Again, as Conner mentioned, we're here to answer any questions.